Alright, so now let's practice some questions on memory complexity. This is the first question where you have a function f that receives an integer n. If n is equal to 0, then it doesn't do anything. Otherwise, it call itself for n minus 1. This is a typical linear recursion where the function is calling itself for n minus 1. First, the function is called for n, then the function is called for n minus 1, then the function is called for n minus 2, and so on. The function in total will be called n times, and every time the function is called, a stack frame is created, and that stack frame takes constant memory. Therefore, the total memory taken will be some constant into n, which is big O of n. This is the correct answer. Let's take the next question. This is the next question, and this is a tricky one. Here also, you have the function f that receives an integer variable n. The function stops when n is less than or equal to 1, which means that it is stopping at n equal to 0. But here, the function is calling itself twice. Had it been a question of time complexity, then the recursion would be t of n is equal to 2 times t of n minus 1 plus constant. And the result would have been on the order of 2 raised to the power n. If we look at it from the memory model point of view or from the function call tree point of view, then first the function is called for n. At the next level, there are 2 function calls for n minus 1. At the next level, there are 4 function calls, each for n minus 2. At the next level, we have 8 function calls and so on. Therefore, this is an exponential growth. At the first level, the total time taken is constant. At the second level, the total time taken is 2 constant. So at the first level, you have 2 raised to the power 0. At the second level, you have 2 raised to power 1. At the third level, it is 2 raised to power 2. At the fourth level, it is 2 raised to power 3 and so on. At the last level, it will be 2 raised to the power n. The total time taken by this function is sum of this entire GP series, which is 2 raised to the power 0 plus 2 raised to the power 1 plus 2 raised to the power 2 plus 2 raised to the power 3 plus so on up to 2 raised to the power n. We know that the sum of a GP series is equal to a into r raised to the power n minus 1 divided by r minus 1. In this case, a is 1, r is 2. And instead of n, we have to use n plus 1 because the total number of terms here are n plus 1. You can do the mathematics and figure the answer. But the question is not about time complexity. The question is about memory complexity. How much memory are we taking? So let's look at the memory model. First, the function is called for n. Then from this function, the function is called for n minus 1. When this function returns, then the function will be again called for n minus 1. Now the stack frame of the second function will be created at the same place where the stack frame of first function was there. If this is the first function and this is the second function, when the first function returns, only then the second function will be called. So when first function returns, the stack frame of the first function will be deallocated, and when second function is called, the stack frame of the second function, which also receives n minus 1, is created at the same place where the stack frame of first function was there. So let's draw the same function call tree again. First, the function is called for n. In the next level, the function is called for n minus 1 and n minus 1 2 times. Then in the next level, the function is called 4 times, and each time the function is called with the value n minus 2. Now at this level, there is only one stack frame. At this level, there are 2 stack frames getting created, but these 2 stack frames are not getting created at the same time. First, the stack frame of this n minus 1 is created. When this function returns, then the stack frame of this n minus 1 function is created at the same place where the stack frame of the first n minus 1 was there. Therefore, the total memory at this level is also constant. I hope you understand. If you are allocating 2 variables at the same time, then you need 2 memory locations. But if you are allocating memory to only one variable, and when this variable deallocates, then you are allocating memory to the second variable, then you are essentially consuming the memory of one variable only. Because at the same memory location, first the memory for first variable is allocated, then at the same memory location, the memory of second variable is allocated. So this is what is happening here. At the next level also, first the function is called for this n minus 2. When this function returns, then the function is called for this minus 2. when this function returns and this function returns, when the function is called for this n minus 2, then the stack frame of even this function is created at the same place where the stack frame of these two functions was created. Therefore, stack frame of all the function calls at one level is created at the same place. Therefore, the memory consumed for one level, for this level, is also constant. At every level, we are taking constant memory. You can look at it this way also, that the maximum depth of the function calls is not more than n. First the function is called for n, then n minus 1, then the function is called for n minus 2, then the function is called for n minus 3, and so on. At the end, the function will be called for 0. So the depth of function call is order of n. Here it is exactly n plus 1, but this is order of n. Now when this function returns, then only then the second function will be called. Similarly, when this n minus 3 returns, only then the next n minus 3 will be called. Therefore, the space complexity in this case is big O of n and not exponential space complexity. This question will be very helpful in binary trees also. Imagine you have a binary tree. If you want to do a pre-order traversal of this binary tree, then the pre-order traversal of this binary tree will take order of n time, where n is the number of nodes in the tree. But what is the memory complexity of the pre-order traversal function? First, the function is called for a. So let me take a smaller tree. So in this case, first the function is called for a. Then from a, the function is called for b. From b, the function is called for left side of b, which is null. When this function returns, then the function is called for right side of b, which is also null. When this function returns, then b will also return. Now when b also returns, then the control comes to a. Then a will call the pre-order function for the right child. When it calls for the right child, then the stack frame of c is created at this place where the stack frame of b was created earlier. So the stack frame of c will be created here only. I am just marking it yellow, or maybe let's mark it blue. So I'm just marking it blue. Then the pre-order traversal for left child of c will be called, which is null. The stack frame of left child of c will be created at the same place where the stack frame of left and right child of b was present. Now this function will return and the pre-order function will be called for the right child of c. When the function is called for the right child of c, then the stack frame of this right child is also created at the same place. So all of these nodes which are at the same level have their stack frames created at the same place. So they share the same memory. Therefore, the total memory taken by this function is big O of height of the tree, which is log of n if the tree is balanced. Mind it, I am not saying that the total number of stack frames created is log n. The total number of stack frames created is obviously order of n, because we have the stack frame created for every node of the tree. What I am saying is that at the peak of memory, the maximum number of stack frames allocated in the stack area are not more than the height of the tree. Therefore, the pre-order traversal, in-order traversal, post-order traversal of a binary tree has a memory complexity of height of the tree and not big O of n. Let's go to the next question now. Alright, what is the space complexity of this function? In this case, you can see that you have a function f and the function is called twice from inside. This is a typical divide and conquer function, and the recurrence equation for this is Tn is equal to 2 times t of n by 2 plus constant. If we have to draw the function called tree, then first the function is called for n. From this, the function is called for n by 2 and n by 2. Then from these two functions, the function is called for n by 2 square, and the total number of times the function is called is 4. Similarly, we will keep on calling the function until n becomes equal to 0. Therefore, the height of this tree will be log of n. Because the height of this tree is log n, you can conclude that the total memory taken is also big O of log of n. Obviously, the time complexity in this case is big O of 2 raised to the power n. So this is the time complexity and this is the space complexity. And that is why I say that to find the space complexity of the function, you should either use the memory model or the function call tree. Next question. What is the space complexity of this function? Here also we have a function f. This function accepts one variable n, and then this function allocates a memory which is equal to theta of n, and then the function call itself for n minus 1. Let's draw the function call tree. First the function is called for n. This function takes big O or theta of n memory and then the function call itself for n minus 1 and n minus 1. At this level, because there is only one function call at one time, therefore we can say that the total memory consumed at this level is also big O of n. Consider it like this, that first the function is called for this, it will take order of n memory. Then when this function returns, which means that the stack frame of this function will be deallocated, which also means that the memory used by this function is deallocated. So when this memory is freed, then the function is called for this function, which will again take n memory. So first you have an array of size n minus 1. This should be n minus 1. Then this is deallocated, and again you have an array of the same size n minus 1. The total memory at this level is order of n minus 1 only. So let's call it big O of n, but exactly this should be n minus 1. What is the memory consumption at the next level? At the next level, there are 4 function calls. Each function call is called for n minus 2. And when one function returns, only then the second function will be called. All of these functions will allocate memory that is equal to n minus 2 into size of integer. Therefore, the total memory taken at this level is also order of n minus 2. The same thing can be said for the next level. In the next level, the total memory used will be n minus 3. We will keep on calling the function until n becomes equal to 0. At the end, the memory will be constant. Therefore, the total memory consumption is n plus n minus 1 plus n minus 2 plus n minus 3, which is summation of n, which is big O of n square. So this is the memory complexity. This function takes big O of n square memory. What about the time? Because this is exponential growth, you can conclude that the time taken will be exponential. How about this function? The difference between the previous function and this function is very subtle. In this case, the memory is allocated after the recursion and not before the recursion. Let's draw the function call tree. First, the function is called for n, but this function will not allocate any memory and call the function for n minus 1. Now, this function will not allocate any memory and call the function for n minus 2. Similarly, this function will also not allocate any memory and call the function for n minus 3 and so on. Let's assume the value of n is 4. So what happens is that first the function is called for n equal to 4. This function does not allocate any memory and call the function for n equal to 3. Then this function also does not allocate any memory and call the function for n equal to 2. Then this function also does not allocate any memory and call the function for n equal to 1. Similarly, it calls the function for n equal to 0 without allocating any memory. Now when n is 0, then this function will just return. This function return to the function where n is 1. Now before returning, this function is allocating memory. So this function allocates n memory, and after allocating the memory, this function returns. When this function returns, obviously this memory will be deallocated, and the control will come to the function where n is n minus 2, where n is equal to 2. Now this function will allocate memory, and then after allocating memory, this function will also return, and the memory allocated will be deallocated. Again, the control comes to this function. So this function before returning will allocate memory and then returns. So when it returns, the stack frame will be deallocated and this memory will be deallocated. Similarly, the last function, this memory will be deallocated, and this stack frame will be deallocated, but before returning, it will allocate memory of size n. So what can we conclude about the total memory taken? See, these stack frames are taking n memory. So the memory taken by the stack frame itself is n. At any point, there is only one array. When this array was present, these arrays were not there. When this array deallocates, only then the control comes to n minus 2, and then this array will be allocated. So at any point, only one instance of these arrays will be there. Therefore, the total time taken will be n plus n, that is 2n. 2n is also big O of n. Therefore, B is the correct answer. In the previous case, the function was allocating memory to the array before calling itself. Imagine if this statement is before recursion. If this statement is before recursion, then what happens is that the function where n is 4, so let me just rub it all. So in this case, the function where n is 4 will allocate memory of size 4 and then call the function for 3. This function will allocate memory of size 3 and then call the function for 2. This function will allocate an array of size 2 and then call the function for 1. This function allocates array of size 1 and then call the function for 0. And then this function will return. At this point, there are n stack frames, and the total amount of memory used by these arrays is also summation of n, which is big O of n square. Therefore, the total memory taken will be n plus big O of n square, and because n square is a dominating factor, the total memory taken will be big O of n square. I hope you are able to appreciate the difference between the two. Alright, so the last function. This is similar to what we discussed earlier. The only difference here is that the function is called twice, but it does not make much of a difference in the memory complexity. It will be a differentiating factor in the time complexity. The function is first called for n. Now this will allocate a memory of size n and then call the function for n minus 1. Now this will allocate memory of size n minus 1, and when this function return, then the function will be again called for n minus 1, which will again allocate n minus 1 memory. But as we have discussed earlier, the total memory allocated on this level will be n minus 1 at any given time. I mean, total memory allocated will be n minus 1 plus n minus 1. But at one time, the memory allocated will be only n minus 1. So it will be memory of size n minus 1 allocated by this function, then deallocated when this function returns, and then memory of size n minus 1 allocated again by this function, second function. So the memory allocation at this level is n minus 1. Then at the next level, the function is called 4 times, and every time the function is called, it will be called for value n minus 2, and it will allocate an array of size n minus 2. The total memory at any point inside this level will be n minus 2. And we can go on like this. The total memory taken will be n plus n minus 1 plus n minus 2 plus so on, which is summation of n, that is big O of n square. Therefore, A is the correct answer. I hope you are able to understand the difference between time complexity and space complexity of recursive functions.